Section 3.1 is titled Numeration Systems. Numeration meaning number. And we're actually going to start by recognizing that there is a name for the numeration system that we use. It's actually called the Hindu-Arabic numeration system. The numeration system was developed by the Hindu and transported to Europe by the Arabic. Some properties of our system that you know very well is that all of our numerals are constructed from 10 digits. Those digits start at 0 and end at 9. So 10 is not a digit, it's a 2-digit number, right? Digits are single. And then the place value is based on the powers of 10, the number base of our system. So do you know why we have a base 10 number system? We have 10 fingers. That's exactly why. So if God had made you with 8 fingers, I guarantee we would be doing a base 8 number system, which would. So it's a base 10 number system because of that. That's how it developed. So this powers that we use, our powers of 10, think about the fact that if somebody gives you the number, and I'll just make one up, that 4 has meaning apart from the fact that I have 4 fingers up, right? The location where it is tells you its value as well. It's in the hundreds place. So I have a base 10 number system where each of those single digits means something different based on its location. So if I shuffle the number up and I put the numbers in a different order, it's a different number completely, even though it has the same digits. And I'd like for you to recall this fact. We've talked about this before. We will talk about it more later on. That when we have a to the power of n, it means a multiplied by itself multiple times. So when we look at, say, for instance, that number 4, this is in the hundreds place, but 100 is a power of 10, it's 10 squared. So when I talk about it being base 10 or powers of 10, that's what I'm talking about, is from the perspective of exponentials. So what we're going to spend a lot of time doing in this section is exploring some of the other number systems that predated ours, and how those numbers would have been represented, how we can go between their system and our system and use that information. So the first system that we're going to take a look at is the Egyptian numeration system. And I know a few of you have done contemporary math with me in an online format because I've done it recently and some of your names have filtered through. So you might notice some of this will feel familiar in this section of material. I will say that our textbook and the contemporary math system that I use, their symbols look a little bit different. So there are, what do I have here, 7 different symbols we're going to take a look at. And they each have different values. So the first one, the Egyptian numeral, is called a vertical staff. And it has the value of 1. So that's easy to remember. It looks like a 1. The second one is called a heel bone. And a heel bone has a value of 10. Now, they don't have a base 10 number system the same way we do, where every place value, it's not like that. But they do build upon the number 10, as you'll see as we go. The scroll that you see here is actually a value 100. So the powers of 10 are going to show up over here in my values column, but they're going to be presented differently within their system. The next one is called a lotus flower. That's the one where the drawing starts to be a little bit like time consuming, is when you get to the lotus flower. So what do you suppose its value is? 1,000. Yep, it's 1,000. The next one is called a pointing finger. Do you have a question, Jordan?
For tests, are we going to memorize how to draw them as well?
I'm so glad you asked. No, you do not have to memorize the Egyptian numerals or the others that we're going to encounter. So when you get to the test, you'll get this sheet of paper. I just keep it in my notebook. And it has all of the values and their names and the equivalent. So like it'll have this table for every table that I use, but it won't have some of the other details. Like it won't say, for example, when we get there, that it's a base 60 number system. Those are the kinds of details, but it will have the symbols. So I don't need you to spend time on your note card at that point writing symbols down. And we'll talk about that again when we get to the test. But yes, you do not have to do that. Okay, so the pointing finger, it's a little awkward to draw. I don't draw that one very well for some reason. What do you suppose its value is worth? It's 10,000. The next one, sometimes it's called a tadpole. Sometimes it's called a burbo fish, or our book calls it a pollywog. I don't really know why they keep changing what they're called. There's probably not a direct translation or something like that into English. But it kind of looks like a little tadpole or a little fish. And it's worth 100,000. And I really think that the astonished man is truly astonished because he's worth $1 million. It might be worth noting that there's nothing that gets any bigger than $1 million. But that's probably okay in most situations. I mean, like, how often do you guys really work in real life with anything that's bigger than that anyway? Probably not even that big, right? So that's a drawback, but maybe not a big one. Something else that you might notice is that there's no value for the number 0. There's just nothing. This one definitely has some drawbacks too as we start to write it out. So what we're going to do is we're going to take one of their numerals. I've drawn it on here. And we're going to figure out first what comes before this value, and then what comes after this value in their system. Okay? And then our third thing we're going to do is to actually convert it into our numeral system. So if you think about what we do in our system, if we want to go up or down a value, is it only affects our last digit, right? I mean, if you're 23 years old, then the next year you're 24, but it's only the 3 that turns into the 4, the very end number that gets affected. And the previous year you were 1 less than that, it only affects the ones digit. So in a very real sense, whatever your smallest value is, which in this case would be our heel bone, because that's the smallest symbol here, is the only thing that's going to be adjusted, or at least most likely, but that's where our adjustment will happen. So what is that heel bone worth? Do you remember? It's worth 10. So if I want to find the number that comes before this, then that 10 needs to become a 9. And what would 9 look like in that system?
9 and the 30.
Right, so the 3 scrolls would stay the same at the beginning. And now I'd have 9 vertical steps. All right, so what would I do for the number that comes after in this system? Yeah, so I'd leave the heel bone in that case, right? 3 heel bones, or 3 scrolls. I'd leave the heel bone, and then I'd add 1 more after it. And then we're going to take that value, and we're going to turn it into our value for it. So we already wrote down up there at the top that the heel bone was worth 10. How many are this, or what's the value of a scroll? It's 100. So how many scrolls do I have? 300. So I'm just going to write this out so that we make sure we're seeing it. There's 3 scrolls, so it's worth 300. And then I have the heel bone, and it's worth 10. So this numeral is actually equivalent to 310.
My first thought was that we'd be multiplying them together, but if we ever need to do that, will it be, like, mentioned?
So explain to me why your first thought has to do with multiplication, Gracie, so that maybe I can get a perspective.
Because there was no, like, plus sign in between.
Okay.
So, like, I was just assuming that.
Yeah, that's what I thought you were going for.
Yeah.
So every numeration system has its own symbols, right? So they wouldn't have had an addition symbol. Like, that's not a thing. That's our convention, right? In the Hindu Arabic numeration system is the addition symbol. So even when I wrote the addition down here, I was doing so because I turned it into our number. So in their system, they simply write the digits right beside each other. And I didn't mention it, but you might have noticed they always write the biggest digits first and then the smaller digits, and they go downhill after that. So as we take one of our values and turn it into theirs, you'll see us doing that. So we have now the number 23,145. And so we're just going to go place value from the left down. And so the 2 in that location is worth how much?
10.
It's the 10,000s place, so I have 2 10,000s. And what shape do I need to use for the thousands?
The pointing.
Or for the 10,000s? Right, the pointing finger. So I need 2 pointing fingers. Told you I don't draw those very well. What will the 3? 3 lotus flowers. don't know. They aren't great, but they're something like that. 3 lotus flowers. How about the 1? 1 scroll. What's next? The 4. 4 heel bones. And the 5? 5 staffs. So I kind of feel like this system is really easy to move in and out of our numbers. That's a benefit. Give me just a second, Emily. But it's very lengthy to write numbers out, especially the bigger the value is. So if you had like 99,999, it would be atrocious, wouldn't it? It would be bad. Emily?
I was just going to say, if it's like, do we have to write them side by side, or can we do like 2 on top, 2 on bottom?
So everything that I see in our book has them written side by side. There is one of them that they start stacking, but it's not in the Egyptians. It's a different system.
Okay, so like on the test, would I be able to stack them? Like for the 4 and 5, could I do like 2 of the heel bones on top and 2 on bottom, or do you want it all?
So I think you're asking that if you did this and right here you did like this, would it be okay with this in front of it and this behind it, something like that? Is that true? I mean, with all the other surrounding pieces?
Yeah.
So yes. The one thing I don't want necessarily to have happen, because it starts to look really confusing, is let's say you did this. Okay, I didn't mean to grab all of that. This is what I meant to grab. So that's probably a bad idea.
Okay.
And the reason it would be a bad idea is because now it looks like 2 separate numbers completely.
Okay.
But do you see how when I wrote it before, when I was describing, hey, if you did it like this, that would make kind of sense. You can identify why that's all going together.
Yeah.
Because if it's still going linearly, and that would be okay. So yeah,
I could like stack
you could do that.
together.
Yeah, like that. You could. Any other questions about the Egyptians? Okay. Egyptians is by far the easiest for us to go in between from our system to theirs and vice versa. The next ones are the Babylonians. One of the beautiful things about the Babylonian system is they only have 2 symbols. That has benefit and it has drawback. So there are only 2 symbols. One looks kind of like a triangle that's sort of upside down or pointing downward. The other one looks kind of like an arrowhead that's pointing to the left a little bit. As you're drawing these, if you don't want to fill them in, it's perfectly fine with me if you have an empty triangle as you're drawing it, or if you use just a pointing, like it looks like a less than sign or whatever for the arrow instead of shading it in. I'm okay with that. It's an abbreviation of what they're doing. We'll be all right with that. The value of each of these are 1 and 10. So you kind of see that 10 popping back up again. But obviously, that leaves you sort of questioning, well, what do you do if a number is bigger than 10? Like, there's a lot of numbers that I would need. Not, 1,000,000 I was good with. I can write anything I want under 1,000,000. I mean, that's not a problem. But 1 and 10 does not seem to be enough. So they compensate for that because they have a place value system, right? The Babylonians didn't do that. We do. We only have 10 numerals, but we have a place value system where the 4 in the hundreds place means something different than the 4 in the thousands place, right? So they have a place value system as well. But their place value system is not a base 10 system like ours. It's a base 60 system. So it's kind of like having, so we would normally have, a ones place and a tens place. Like this would be 1, and this would be 10, and this would be 100, right? That's what our place values kind of look at if we kind of write them out in long form or expanded form. Well, theirs look like this. They look like 1, and then they look like 60, and then they look like 3,600, and the reason they look like 3,600 is because that's 60 squared, just like 100 is 10 squared. So each of their place values is actually built upon the base of 60 instead of the base of 100. And then within each of their place values, they will add whatever tens and ones they need to actually equal that value. So let me show you an example of one of their numerals so you can see how that plays out. So it looks very different, right? Lots of triangles and arrows. Now, kind of like with the Babylonians, where a bigger symbol comes before a smaller symbol, that happens here as well. So this is a symbol of 1, and this is a symbol of 10. But if the bigger symbol is supposed to come before the smaller symbol, right, like that's how it's supposed to be, then when you see them in reverse like that, that means the place value changed. So imagine now that this is a place value, and the next one would start right here. And it would actually continue all the way over to the end, because I don't have that, nuance happening again, or I have a triangle in front of an arrow. I don't have that. So this would be actually let me just draw it in here like this. A 2 place value number. This is the ones place, and this is the 60s place. So can you count for me how many are over here in this place value? So just so we can have a reference point. What's over here?
59.
It is 59. Okay, there's 5 arrows, that makes 50, and then there's 9 triangles. Okay, so we're doing the same kind of questions we did on the previous number system. Find the number before, find the number after, and then turn them into our number system. Okay, so if you were to find the number before, then the ones place, right, where it's got all the symbols that add up to 59, has to be decreased by 1. How would you do that? Yeah, you just take away triangle, no problem. So we would draw the original triangle, we draw our 5 arrows, and then we draw, instead of 9, we draw 8 triangles. Oh, 8, sorry, there we go. That would be the number before. So in all of these, I'm always asking you questions of what comes before, what comes after. And one of them is always a little bit awkward. So over here when we did the Egyptians, the awkward one, when we're back, was the one that was the what comes before. Because we had to take a heel bone and we had to break it into 10 vertical staffs and then take a vertical staff away. We had to regroup is what we really did. I mean, we do it in our system too, we just don't think about it that way. But we regrouped it. So over here, I didn't need to regroup to remove something. I could just take that one off. It was no problem. But what would have to happen to make the 59 in the ones place 1 bigger? You would think about adding one of the triangles. But now how many triangles do you have?
You have 10.
10. You have 10 triangles. You're thinking about arrows. Those of you who said 6. You have 10 triangles. But 10 triangles equals 1 arrow. So now you don't have any more triangles. You have 6 arrows, right? Which is 60. And we're in a base 60 system. So, right, like once you get to 1, like if you have 10 $1 bills in your wallet, it probably bugs you. Doesn't it? You're like, man, just change it in for a 10. This is taking up too much space. Same thing. I've got 6 arrows now, and it's a base 60 system. So what do? Well, I regroup, and I carry it over to the next column, just like we would do. There's a problem with that, though, because the next column, which had 1 arrow or 1 triangle in it now, would now have 2 triangles. And this would be the correct symbol. But they don't have a 0. So what do we do? So that's actually the next question that pops up on your question set is, but how else could we interpret that value that we just found in part B? 2. That's the first one that you might think. And you might think, okay, well, yeah, but it actually would also be the same as the number 61. Right? If you had the number 61, you'd have a 1 in the 60s place and a 1 in the ones place. 61 would look just like it. So you've got a symbol, this one over here that we found on part B, 2 triangles. That means 120. I mean, that's really what we just found. It means 120, right? 2 60s. It also means 2. And it also means 61. And plenty of other things because there's the 3600s place and so forth. There's probably a reason this didn't stick around, don't you think? Right? It leaves room for a lot of ambiguity. So this is a problem. So that's a drawback. I mean, so there's a drawback in this system because you don't have a place value of 0. I mean, you don't have a numeral for 0. That's really the problem. If we had a 0 we could put in there, we could fix that part, right? If I could put a 0 in the ones place, then I'd know that both of those digits over here were in those places. But it doesn't fix everything, because then how do I know that both of those digits side by side aren't maybe like in the 60s place and the 3600s place? So even that wouldn't be enough to fix all the problems. Emily?
Is the 2,61 like 2,000?
No. There are two numbers. There are two different numbers that this could be.
Okay.
There are two different options, at least. I mean, those are the two that I found first that are other things that would mean. Okay, so let's actually do this numeral. That is the numeral we were actually given right up here in our number system. So we've already written down a fair bit of this. We have the 60s place, and there's a number 1 in it. We have the ones place, and there's 59 in it. So in a very literal way, we have 1 times 60, and we have 59 times 1. So the 60 and the 1 are the place values where they reside, and then the number next to it is the numeral that it gives us. So this would be 60 plus 59, which is 119. So this numeral that I was given over here originally is 119. So now we're going to go the other direction, where we're going to take one of our numerals, right, and we're going to turn it into Babylonian. Okay, so we have the number 43,205. And all we've got are things with tens and ones, right? But we have the place value system to help us out too. So let's just remember real quick what I wrote on the previous slide, where there's a ones place, and then there's a 60s place. And then there's 60 squared, which is 3,600, just as a reminder. And if I went one bigger, we can see whether or not it would be included. 60 cubed. And that's 216,000. Now, I don't have a number that's that big. My number is in the 10,000s, not in the 100,000s. So this won't be necessary. I will have a 3 place value number. Okay? I will need things in the tens, or in the ones place, in the 60s place, and in 3600s place. So I want to show you, I call it a division algorithm for working with these. It'll work for all the problems we do, so that makes it very friendly. You do need to know the place values in order to do this. So I need to know 3,600, 60, and 1. Okay? So before you start this, you need to know those values in whatever system we're working in. And what we're going to do is we're going to take our 43,205, and we're going to divide it by the biggest place value that I'm working with. So that's why I can't use the 216,000, right, because it's too big. So I start with the 3,600. And I need to know, and you're welcome to grab your calculator to find out, how many whole number times will 3,600 go into 43,205? What's the whole number that comes apart? It's going to have some decimals, but I don't care about that. 12. So this is 12. And we're just going to write the 12 over here. I don't want to write it on top because I'm about to stack my divisions. Let me show you. What is 12 times 3,600? 200? Okay. So I'm going to stack this right here. That leaves me with 5 left over. And I've got that second, it looks almost like stairs or something going on over here. Okay? So I've done subtraction just like with normal division right here. And I've got 5 left over. Okay, everybody good so far? All right, what I'm going to divide by next is the next place value. I know it's not going to go in, and that's okay for what we're doing, but we're going to represent it in the division algorithm for some of the other operating systems that do have zeros. So I want to show you something that works for all of them. So we're going to divide by 60 next. Of course, it goes in 0 times. I multiply, I get still the remainder of 5. Okay, so it's not a very exciting step. And then my last step is to divide by the last place value, which is a place value of 1. Of course, it goes in 5 times. I subtract my 5, and I get 0. So I'll always get, when I'm doing this, remainder of 0 at the end. So 2 things tell you you're done. You've got a remainder of 0, and you had the last division by the place value of 1. Now, these values over here actually tell you what goes in each place value. So in a very literal sense, I have 12 360s, I have 0 60s, and I have 5 1s. Now, that still is not in their number system, but it tells me how I write those numbers. And so I have 12. How do I write 12 when I have these digits? Right, an arrow and two triangles. So I'm going to write an arrow and two triangles, and that's the number 12. I don't have any way to write 0. There's just nothing. So I just keep moving. If you want to leave a space, you can, but it still doesn't really mean anything. So we just keep going on, and then we move into having the number 5. And how do I write the number 5? 5 arrows. Yeah, 5 triangles. Yeah, I knew what you meant. Thank you. 5 triangles. Now, of course, the problem is that because I don't have a 0 in that 60s place, this also could mean 12 60s, right? And 5 1s. And if they were a little too close together, you might really just look at this and say, hey, it's 17, right? There are inherent problems in the system that we can't fix. They're just there. Okay, any questions about the Babylonians? Hallie first.
Going back to the division.
Yes.
The second step, where you divide by 60 and 0, where does the 0 come from?
Well, just that 60 doesn't go into 5. This is the number that goes into it. So like 3,600 goes into 43,000 12 times. 60 goes in 0 times 5 went in 5 times. Or 1 went in 5 times.
Okay.
Yeah. So the numbers on the right here that are showing up are where our numbers would normally be on the top of a division division like bar normally. I just don't have space because I'm continuing it down the line.
So you're dividing each by the, so you have the 3,600.
Yes.
One in those places.
Yeah, so this is really just 43,205 divided by 3,600, 5 divided by 60, and 5 divided by 1. Abigail.
After example 3, how are we supposed to know exactly what the number originally is?
That's a really good question. So how do we know? We will put in the minimum number of places where we know they had to have a break. So where I drew my red line right here has to be a break. There has to be a place value change because it's a smaller numeral in front of a larger one.
Okay.
Everything else is speculative. Maybe there is another break. I don't know. But we have to all decide that we're going to do it the same way. Otherwise, almost any answer is right. And that doesn't seem to sort of resonate either. So we're only going to make the place values break where they have to break when we're interpreting them. Okay? All right, we're going to do one other number system today. We're looking at the Mayans. All right, so the Mayans actually have 3 symbols. And that third one that looks like kind of like a clamshell has a value of 0. So we finally have a 0 placeholder. That's progress, folks. Because the last 2 systems didn't have that. And that wouldn't have fixed everything about the last 2 systems, but it would have fixed some things. So we do have a 0 now. The dot has the value of 1. And that vertical bar has the value of 5. They have a place value system as well. Their place value system is a modified base 20 system. I'll tell you what that means in a second. It's written vertically. So instead of writing their numbers from left to right like we do and like the Babylonians did and like the Egyptians did, they write them from the top to the bottom. So the bigger place value is on the top, the smaller place value is on the bottom. So it's written vertically. And then they put their dots on top of their bars. So if you had the number 6, you would have a dot on top of a bar. That would be 6. So let's talk about what modified base 20 means. So if it were base 20, it would be like we had with before with the 60s. We'd have the 1s place, the 20s place, the 20 squared, the 20 cubed, and we'd keep going, right? Well, their modified base 20 system has the 1s place, and then it has the 20s place. And I'm writing them from the bottom up because that's how their numbers are going to line up. Bottom is the lowest value, and then the next place value is 20. Then we're going to go up from there. But the next one is not 20 squared. It's 20 times 18. I'll get you back to the second why that's happening. And then they would go on with powers of 20 after that. 20 squared times 18, 20 cubed times 18, and so forth. That happens after that. So let's actually multiply out what their values are to get some sort of sense of what's happening here. So this is the 1's place, of course, and this is the 20's place. What is 20 times 18? 360. And that right there is the magic reason why they use 18. So 360, what are things you know that have to do with 360? Okay, degrees in a circle. And there's one other.
Days in the year is 365.
And that's exactly right. It's approximately the number of days in the year. It's really close, right? We're talking ancient civilizations here. And the Mayans, as you know, were the ones who had, predicted the end of the world in 2012, right? Because their calendars. So they were very into calendaring, very into doing things with, the cycles of the moon and the sun and stuff like that. And so that 360 came about from that. That's why they want that in there, is because of the way that they thought about kind of the universe. So as we build upon that, what would the next one be? If you take 360 and you multiply by 20, what do you get? I don't have this written down. Somebody's got to tell me. 360 times 20. Is it 7,200?
Yes.
And the last one, 20 cubed. So take 7,200 times 20 again. What do you get? 144,000. So we won't see anything any bigger than that, but the powers of 20 would just increase, and so we can continue that on. So that's their place system. It's a little bit different. So let's take a look at an example in their place value system. We'll look at what comes before and what comes after, and then some inherent problems and what this happens if we... Okay, so when I look, this is kind of like your question, Abby, is how do I know where to break things apart? So dots are always on top of lines. That's always the case. So anytime you see a line and then a dot below, the place value has to break. So there has to be a place value break here because dots always go up on top of the lines and within a single place value. Everybody good so far? Okay, so again, just like in our system, if we're wanting to increase or decrease something, we do it to the lowest place value, right? So we take our lowest place value. What is the number, right, the value that's happening down here? It's 9. So what would we do to find the number before? We take away a dot. You bet. So previously I had 2 dots and a line. So those stay. And then I take away one of the dots. There were 4. Now there will be 3. 3 dots and a line. That's the number before.
Can you explain that a little bit?
Yeah, so this right here is the number 9 at the end.
Yes.
And so in order to make it 8, I just take away a dot.
Why do we need to make it? Oh, because we're figuring out what comes before. Okay.
Yeah. Okay. We're good? So what would we do then if we wanted the number that comes after? You'd add a dot. But now you'd have how many dots? 5 dots. But 5 dot makes a line. Okay. So we have the 2 dots and a line. And then we have... Do you see a problem? Where's the break? How do we know? Because this number looks a lot like 17. 5 plus 5 plus 5, 3 lines and 2 dots. That's 17. That's the problem. And the 0 that we have, which we will make use of in a moment, but the 0 didn't fix this particular problem, did it? And once again, a reason why we probably don't use my enumeration system today. So what is the number that we could have interpreted this to be? Well, we could have interpreted this to be 17. Or, we could say that each of these is in their own place value line, right? Like it could be that this is the 1's place, and this is the 20's place, and this is the 20 times 18's place, and this is the 20 squared times 18's place. We could separate every single one of them. We could, because there's nothing that says we can't. That's a problem, right? So I'm just going to say lots of other options. There's lots of other things that could show up from that. That's less than ideal, for sure. And if you were an accountant or a bookkeeper, good luck. Right? That's not good. Let's turn their number into our number system. We did say that the number at the end, the original number is what I'm looking at, back up here. We did say that there's 9 on the 1's place, right? So in the 1's place down here, it's worth 1. There's 9 of them. Let me write it like this. This is the ones place, and there's 9 of them. And over here in the 20s place, there are how many? What's the bar and the 2 dots? It's 7. So if I use the bare minimum number of separations, which is what we'll always do by default, bare minimum number of separations, there are 7 20s and 9 1s. So I would take 7 times 20, it's the 20s place, plus 9 times 1 in the 9s place. And what would that give me? 149. So we'll pause right there, but what we're going to do next is something very similar to what we did with the Babylonians. We're going to take a number in our system, and we're going to turn it into Mayan, and we're going to do that using that division scaffolding, that algorithm thing that I did on the left-hand side. Okay? And we'll pick up there next time.